Welcome to the Untangling Web3 podcast. So the internet feels like a basic human necessity, something our entire way of life depends on. But how many of us actually understand how it works? As Web3, AI and all immersive tech are growing, so do the demands on that infrastructure. So how does it actually work and who's building the backbone? Enter today's guest, Timothy Creswick, the founder and CEO of Vorboss, London's only dedicated fibre network built specifically for business. With 250 million invested, 700 kilometres of fibre laid, and 100 gigabyte services live, Tim is reshaping how connectivity is built, priced, and delivered. Today, we're unpacking how the internet really works, what Web3 needs to scale, and where infrastructure is headed next. Tim, welcome to the show.
Thanks for having me on. It's actually the first time that I've recorded in this studio.
Really?
Oh, really?
Yeah. Your very own Vorboss studio. It's the first time you've been in here.
It's kind of weird.
Yeah, we can recommend it. It's very good. Yeah, no, it's nice to have you on finally. I mean, we've been talking about getting you on for a while. We've obviously recorded a few episodes in here now, and we're very grateful to have this space. But yeah, we thought, what better place to be talking about the internet, right? Because obviously you guys are an infrastructure provider for the internet, and we've obviously spoken before, and I realized this conversation could go one of many, many different ways. There's so many things we could cover, but let's start with the basics, because when people think about the internet, I think a lot of people just use it and it's like magic to them, right? They don't understand anything that's going on. How would you describe kind of what actually is under the hood, given that you are part of that stack? How would you kind of, maybe not going all the way down the levels, but maybe like just to give you more information than I'm Googling something, right? How would you describe what's actually going on under the hood?
Well, I think, and it's a really interesting point, right? Because I think particularly with Web3, we've got to like a level of abstraction where people just stop thinking about it, and then we get questions like, we get things a lot, which is like, wow, you spent a lot of money building a fiber network, isn't it all just going to go on Starlink? And it's like, so, and I know we spoke briefly like a while back about kind of some of the fundamental physics of this stuff, and it's like really just understanding that maybe starts to, you start to get a better understanding for like what the physical limitations are. There's a lot of people that still don't realize that most of the internet traffic that kind of comes and goes from a continent, in fact almost all of it is on subsea cables. And then there's a lot more people that don't realize that even if you understand it's all subsea, we've had subsea cables since the early 1900s. In fact, the first ones were in the late 1800s. So kind of the technology and the complexity around just some of these kind of insane infrastructure projects.
Yeah. I think some people will even just hear that and think, what do you mean subsea? People won't understand. People will be aware that there's stuff going on under the sea to make the internet work, right? That's in itself is an insight, I think, that people will be surprised about.
Yeah, so I think, maybe to come back to your question, if you think about, so there's a couple of things, right? Which is that the internet, one of the fascinating parts is that there is no kind of not-for-profit element to that, right? Like it's not like it's broadly not really coordinated by national governments. It's not like it's a UN-controlled entity or anything like that. The internet is just a collection of private companies that agree to work together. And in a weird way, that's kind of strange that it works. You can kind of understand with things like, I don't know, your mobile phone. If you're on one mobile phone network, you go to another country. There's a roaming agreement that allows you, you see a different network pop up on your phone, and you can kind of understand that's because your mobile network has some agreement with that mobile network. You probably don't understand the crazy stuff that's happening behind the scenes to make that actually work, but it does work. And I think, really ultimately, there's no obligation for that to happen. Like the company that you work with, your domestic mobile provider, understands that they'll win more customers if when you travel you don't just have no reception. So they see a commercial benefit to doing it, and then they presumably have to reach a commercial agreement with foreign networks to agree, if we have lots of subscribers in your country, you have lots in ours, maybe there's an exchange, whatever. And essentially it's like that. There's lots of these bilateral agreements that basically power the internet.
And I guess there's a lot, and you're saying it's a private endeavour mostly, but there's obviously a lot of government involvement, right? Be it regulations, maybe we can talk about things that happened with Snowden and like say dependencies of governments knowing how much they need internet, especially when we say incidents like deep sea cables being cut by foreign operators and all this kind of stuff, and maybe we can touch on that a bit later. But before we go into that stuff, you're talking about deep sea cables, most of the internet basically going through these. But when I use my phone, when anyone uses their phone, they think wireless. They assume everything's wireless, and obviously Starlink has kind of perpetuated that opinion. Can you give us a really simplistic breakdown of when I message someone on their phone in the US, how is that data going from my mobile device to their mobile device?
I love questions like this. So that's actually like a really nice one, and the mobile one's a great one because it kind of covers both of those. And actually, to your point you just made, that there's way less government involvement than you would think. We'll come back to that. But Sure. So, if you pick up your phone, send a WhatsApp, I think everyone now gets that that's actually a data connection, right? That's not using, and that in itself is another debate. But so pretty much what's happening there is, if we skip through it very quickly, there is the what we call the air interface, which is your phone using a radio to communicate to a cellular base station. Typically, that's like a macro tower. If we're in London here, it's going to be on top of a building nearby, most likely. And so that kind of that packet's hitting that station at that point. So we're really talking now, particularly with 5G, those distances are way smaller than they used to be. So there's more base stations. So you're within a few hundred meters maximum in an urban environment before that signal lands on something where it's then connected over physical fiber links.
And just a quick question. So the shorter distances, does that mean we can go higher frequency so we can send more information per packet?
That's pretty much it, yeah.
Okay.
So with there's a ton of physics involved, and that probably needs a whole separate podcast for someone. But fundamentally with 5G, and actually we're not using all of the 5G spectrum yet in a lot of the world, but by moving into higher frequencies, we can actually push more bandwidth, and then there's a whole thing as well with cellular networks around how you provide that quality of service to large numbers of subscribers in an area. So it's a bit more complex than Wi-Fi, where you maybe only have a handful of subscribers on your Wi-Fi network. You're suddenly talking about having thousands or tens of thousands. So it's a very different kind of radio problem. But yes, moving into higher radio frequencies, broadly speaking, allows you to transmit higher bandwidths. The trouble with higher radio frequencies is they don't penetrate glass walls, buildings. They don't really kind of tend to bend very well.
Okay.
So if you move to higher frequencies, you basically ultimately you get to a point where it's really line of sight.
Okay.
And once you get to line of sight, then you need a lot more base stations. So actually, 5G, and particularly when you start using the actual 5G spectrum, requires a lot more cellular coverage, like physical coverage with base stations. Obviously, if you put more base stations in and you shorten the range, then you have fewer subscribers per cell, which also gives you a better kind of slice of the bandwidth cake, because all those subscribers are sharing some bandwidth. So there's kind of other benefits that come with it.
So we're at the base station now.
So you're at the base station now. Now you've got a fiber connection. So if we're in London, that fiber connection will take you back to some element within the mobile network's kind of core. In London, most of the networks will only have a handful of aggregation sites where they take their traffic back to. So your packet's now basically still in kind of a radio, like cellular format. It's not really as an internet packet yet, but it's now on a fiber leaving the base station and heading back to a data center somewhere in the center of the city, most likely. Pretty quickly at that point, it's gonna turn a few corners through some bits of equipment that basically offload it as a packet on the internet, as a true IP packet, once it kind of leaves the mobile provider's network.
Okay.
And then, probably literally within the same building, there's only a handful of data centers in central London where big providers are exchanging traffic. If you're messaging someone, let's say they're in the US, it's going to hit probably within one or two hops, and by that I mean like it's jumping between a couple of routers, which will be boxes the size of an oven in a data center. You'll have multiple operators sitting in one of these data centers. So, for example, down in the Docklands in London, you've got buildings with several hundred carriers in them, us included. And so within those buildings, it's relatively easy for those carriers to interconnect. So what will happen is that message you've sent now jumps from one router to another, probably gets to the edge of your mobile operator's network, by which we sort of mean it's like we would refer to it as like a publicly peered router. So it's a router that is on the border of their network that now talks to other networks. So that's kind of the least secure part of their network. And at that point, the packet gets handed off based around an understanding of where it needs to get to.
Okay.
So imagine, if we're going to use a much simpler analogy, imagine you have something you drop in the mail, right? And you send something to you send a postcard to Singapore and you send a postcard to Alaska. It gets to a point where it's like, okay, this is not UK domestic mail. So it gets to a point within, presumably, Royal Mail's sorting where all international mail gets aggregated, right? So this is kind of like the provider's border router, where it goes, okay, well, this isn't staying within our network, this is leaving, so I'm going to aggregate it all here. And then you can imagine they start to route those things. All the postcards and all the mail for Alaska starts piling up over here, but maybe in aggregate they say, well, everything going to North America and everything going to Asia.
Got you. Yeah.
Right? And then at some point they hand it off to, they may choose, okay, well, they may fly the mail partway to Frankfurt, at which point maybe an Asian carrier picks it up. And in the case of the North American mail, maybe they don't at all. Maybe the US Postal Service actually picks it up in the UK. I actually have no idea, right? But it doesn't sort of matter. And that's actually analogous to the kind of peering arrangements we have with networks, which is, for example, with Vorboss, if you're sending traffic to Germany, chances are we carry it to Germany for you and then hand it off locally. Okay. But there are other instances where a German network might have a presence in the UK and they'll pick up the packet from us here and they'll transport it. It doesn't, in some ways, doesn't matter. But what you've got is like a table of routing information that says for any destination on the planet, a global router sitting in a data center in the Docklands. So this border router where your WhatsApp message is sitting right now, it has on it a few million routes in memory, which is basically tells it what is the next hop.
Okay.
Yep.
I get you.
Where do I send, for every possible destination on the planet, where do I send this packet? So in your example of texting someone in the US, chances are the next hop is a carrier that either has a strong US presence, is a US carrier, or depending on your mobile network, if they have a presence in the US, it'll send it off to that part of their network.
Via a deep sea cable, I assume.
At that point, yeah. So then it's going to probably hit a carrier that has, there's quite a lot of transatlantic cables. It will inevitably hit a carrier that sits on one of those, has some capacity on one of those cables, and a lot of those cables are shared, they're consortium owned, so it's quite complicated in terms of like who has what capacity where, but ultimately, yes, and then it's going to hit probably 2 more hops before it hits a router that fires it off across the Atlantic, gets picked up on the East Coast, maybe it hits one more network. And for the more technically minded people, if you've sat around and ever done like a trace route of a packet on your machine, you can see some of this. Now, actually, there's a lot hidden from you in that, and sometimes depending on the networks, it's kind of you have a choice as to how much you expose on those, but you can kind of see what networks you're hitting along the way. But what's interesting is every time that packet moves between any 2 networks, there is some sort of commercial arrangement.
Yeah. Okay.
Now, sometimes it's settlement free. It's that we agree we're going to hand you packets, you're going to hand us packets, and we cover the cost of the physical connection between us jointly, but we don't charge each other for bandwidth. And then there are other situations where you have large global carriers who charge basically everyone for bandwidth, and they say, okay, well, we have so much coverage, we can get your packets anywhere. And then the fact that you have global reach is just this kind of interesting, in the same way that you can sit here and be fairly confident you can mail a postcard to anywhere on the planet.
Yeah.
But it only sort of works because at some point there's like a bilateral agreement, right? Like that stamp has to pay the local, some element of the stamp has to pay the local carrier if you send a postcard to Australia.
Yeah, it's kind of amazing that it's all self-organized and it actually does work without a kind of central.
Well, then it works because even if you're in the remotest place, right? Like you have the inverse is true. So if you're in Mauritius, right, and you're connecting the internet, you're a local provider, so you're the small provider there. You have an incentive to be able to provide people global connectivity. So you're probably the driver behind saying, okay, well, we need these arrangements.
Yeah.
And we might have to pay for them because we're small, and there isn't much inbound traffic. But the reality is, there's a need.
Okay.
There's a need for these interconnects.
And I guess I kind of think of it like roads. I imagine that it started with, say, one really strong main road between New York and London for whatever trading purposes. And then eventually you kind of get this spread of other roads being built from those center points that then use the already existing infrastructure and then just build a little bit more.
Yeah, so if you look at a global internet traffic map, it starts to look an awful lot like a global air travel map. Right, and actually with a lot of the same hubs. And that's kind of not a huge coincidence. Like the kind of core interconnect data centers where traffic is exchanged popped up generally near the very big global airports. And for the same reason, right? Because those are and broadly where the population centers are.
Okay.
Yeah.
So that's where the commercial activity was, where the population centers are. And there's a few odd things, like you've got some very large data centers popping up in Iceland because power's cheap. You've got, all of Northern Virginia in the US, which is now a huge hub for data centers, but actually not an interconnect hub. So almost think of that more like a giant freight terminal rather than, or like a warehousing facility rather than where the traffic's actually exchanging or where passengers are. But the 2 maps look really, really similar.
Interesting. It's kind of what you'd expect, I imagine, because because that's where the demand is, right? That's where the human demand for all the traffic is. I want to just quickly touch on, we jumped, in our example, going from the UK to North America or the US, we jumped straight into this point of, okay, it's going deep sea. I think a lot of people, based on, we've not been in school for a while, but your kind of high school education of how the world works, I think a lot of people will think of kind of how GPS works, and they'll think of satellites and bouncing signals up and down. Why is it that the messages we're talking about here are going in these deep sea cables? Is it just to do with latency, or what's the kind of ultimate reason why we're not using a kind of satellite system for this?
Two things. So latency is the kind of the really obvious one. It takes a long time to fire stuff up into a geostationary orbit. So you have, one of the things that's interesting about Starlink is that people don't really appreciate the difference between low Earth orbits and geostationary orbits. I know this is really tedious, but if you think back to when I was growing up in the 90s, and you have you'd have satellite, like everyone had satellite TV, right? And satellite TV is generally broadcast. It's not super latency sensitive because it's a broadcast. You don't really care if you're 3 seconds delay. But it's the way it works is you put a satellite up in geostationary orbit, which means it stays over the same part of the Earth because it's basically rotating at the same speed, and that's actually a super, super high orbit. The trouble with that is then the signal has to travel an extremely long way to reach the satellite and then come back again. What's interesting about and that latency basically makes it broadly unusable for internet. Like real-time communication. It's just really, really super difficult. What's interesting about Starlink is they put stuff in a low Earth orbit. So I have to check, but I think a Starlink satellite is only something like 130 kilometers up.
Okay.
So it's like, for those of us in the UK, that's like closer to us, like closer to us vertically than Cornwall is.
Yeah, it's like Cardiff to London.
Yeah.
And I guess the key point there is the distance, say, going to one of these low Earth orbit satellites from, say, using that to route between New York and London is a smaller distance than, say, using a deep sea cable.
In theory, it could be.
Okay.
Yeah, and I think, well, actually, no, it's not a shorter distance, but it could be low latency. That's another reason. But so we'll come to that. So, yeah, if you can go to a low Earth orbit of something that's 130 kilometers, whatever it is up, then obviously that doesn't take that long. The challenge is that now it's in a low Earth orbit, it's moving at about 22,000 kilometers an hour.
Yep.
So it's only overhead for a very, very short period of time. So a lot of the complexity of Starlink is basically providing you this continuous coverage.
Okay.
So it means that in the same way you get it with GPS, the satellites are only overhead for about 30 minutes max, I think.
Okay.
So then there's this constant handoff having to happen. So that's why Starlink has so many satellites, because basically at any given time there's a whole bunch of satellites in the constellation overhead, and your terminal is having to hand off between those. And that's actually insanely complicated in terms of how that works. It's actually miraculous that they've made it work well. And then all the signals from that get relayed between the satellites. So your signal goes up to a satellite, it bounces around, and then it finds a path through all these other satellites, which could be moving at relative velocities of like 40,000 kilometers an hour. It's completely mad. And then it lands back on a base station, and then we're back to the same thing, which is like your mobile. It gets plugged into a core router and then into a global router, and then it gets routed like regular traffic.
Yep.
So actually, it's no different really than you sending a WhatsApp message on your mobile. It's just that kind of what we call the air interface on the mobile, which is like from my phone to a base station 50 meters away or 100 meters away, is now substantially more. It's like, and it's actually going to a relayed air interface of up to a satellite, and then it's beaming it to another one and to another one and to another one.
It's a lot. It sounds really complicated.
That is really complicated.
Yeah.
The advantage of subsea cables is, but the really big advantage is loads more capacity.
Right.
And I think the easiest analogy I can use is like radio is like if imagine we're in a big room of people and I'm signaling using like Morse code, and I've got a light bulb, like an old school like incandescent bulb, and I'm turning it on and off to signal ones and zeros, right? And I'm flashing it. It's really impossible for that bandwidth is shared between everyone in the room. I can't, if I want to communicate with you and I want to communicate with him, I have to do it like we have to basically somehow signal first who I'm communicating to.
Okay.
And then I can only talk to one of you at a time, right? And if you're each equipped with one of those bulbs to reply to me, we all have to go quiet.
Yeah.
Like no one flashes anything so that you can flash your bulb, and then like you have to just witness it.
Yeah.
You know, and that's how
Not very
radio
private.
and that's how radio works, right? Like that's
Yeah.
how, I mean, you've all sort of used two-way radios or whatever, like only one person can speak at a time on the frequency.
Yeah.
And broadly speaking, that's the problem with your mobile phone, and broadly speaking, that's the problem with Starlink, is that within a given area, you're all sharing this bit of bandwidth.
Okay.
Right. Okay.
Now, in reality, the way it actually works is there's a whole load of, like, imagine like lots and lots of channels, and so there's enough kind of ability to do like clever multiplexing, so you actually sort of can talk at the same time. And then Starlink does some very, very clever stuff with beamforming to say, okay, well, actually, it's like it projects like a cone down onto the Earth and captures a number of subscribers, and then that's spillover. So you can almost imagine now I've got my light, but I've kind of got a cone around it.
Yeah,
it's more like a torch. I'm firing it at you, and actually there isn't much spillover to him.
I understand. Okay.
And so we can kind of do it. Now, if you want to take that analogy all the way to the extreme, well, with fiber, it's like, well, just imagine I had a tube, like a cardboard tube between me and you and me and him. Now actually there's no spillage at all, and actually I can have thousands of these tubes, and I can sit there, and then I can have lots more lights, and I can signal to everybody concurrently with none of this kind of overlap.
I mean, that stuff blows my mind, that we can have these tubes between, like, across hundreds of kilometers and send information from the one end to the other, and it can be received almost instantly.
Yeah.
You can get an absolute, like, gigabytes of data per second being sent. That sounds like magic in a lot of ways.
Yeah, and it is. I mean, it's in some ways insanely complicated, in other ways insanely simple. But we get down to fiber strands that are smaller than a human hair, essentially, and that is analogous to the cardboard tube, right? We take that fiber strand, we can stick a laser on the end of it, and we can happily go actually several hundred kilometers before we need to intercept that signal, and then actually decode it, and if necessary, repeat it. It'll be a couple thousand times less bright, but again, because when you look into the end of that tube, it's dark. You know, the only thing that you're getting is essentially the laser light that was transmitted.
And what's actually changed over the last, like, say, 5 to 10 years? Obviously, you're being a disruptor in the space on the case of, like, infrastructure and fiber providers. Like, has the technology changed that much in the last the recent 5 to 10 years, or?
I think we're in a bit of, like, sort of steady progress, right? So I think it's more like in the last 30 years there's been substantial change, but in the last 5, not really. I think we're pushing the envelope more and more on bandwidth, but there's all these other kind of interesting innovations. So you can imagine, like, very crudely, we have, like, ways we can cram more down it. So if you take my tube example again, right, and I'm flashing a light down the tube, okay, we'll get it. Well, now actually, why don't I have, like, 3 lights with, like, a traffic light with different colors, and now I can flash all the different colors, and you can determine each color distinct from the other one,
embed more information,
so I can now transmit 3 times as much information. Well, okay, that works. Now imagine actually I use, I don't know, let's say 50 or 60 colors, and they're all just ever so slightly different, but you can discern them. Well, that works. But how about also I don't just turn the light on and off? How about I use the light at, like, 3 different levels? And I say, okay, well, actually, I can have it, like, on, off, and half on, and you can calibrate your brightness, even though sometimes you're a long way away. But if you know what bright looks like and you know what off looks like, you can figure out what halfway is, even if you're 100 miles away. So then actually with one turn of the light, I can actually encode way more information. And then you can multiply that.
That makes sense,
So one of those is basically amplitude modulation, and the other one is essentially frequency modulation. And if we bring those two things together, it's quite common that we can do things like what's called, like, 16 cram, which is basically amplitude modulation. So we can have 16 levels of brightness, and we can multiply that out by sending down a whole ton of different wavelengths, so lots of different colors. And so you can see very quickly when you multiply those two things together, you can take the theoretical input, like theoretical capacity of fiber 20 years ago, and you can make it hundreds of times more.
Today's episode is sponsored by the VeChain Foundation.
Now, we often talk about how emerging technologies like blockchain have the potential to revolutionize sustainability, and VeChain is at the forefront of this green movement with initiatives like VBetterDAO. Let's take a closer look.
Imagine tracking small actions like recycling at low cost, making them valuable assets. These verified records build a massive collective impact, benefiting people through their own actions. Sound a bit complex, but VeChain made it fun. Explore our apps at vbetter.com.
VeChain's goal is to power a new era of sustainable solutions. So if you've got an app idea or just want to earn rewards for small, sustainable actions every day, go check out vbetterdao.com to find out more. And now, back to the show.
Do you have a sense for, because obviously we talk a lot about like scaling laws in computer science and technology and how far you can push these systems, and obviously when you're talking about transmitting things over light and wavelengths, you have this kind of infinite spectrum or infinitely divisible spectrum. But do we have a sense for how far we have already pushed the physical limits of how, like the cables that we're using? Is it still lots of room to grow that you're seeing, or are we kind of hitting those limits?
Yeah, if we like really pick up on the semantics of the question, like we haven't really pushed the limits of the cable. Like we've seen that with like research laboratories who are doing really crazy things with the cables. The limitation for the last certainly my whole career in the industry the limitation's always been the equipment. It's like everything. It's like with smartphones, drones, PCs, whatever it is, it's the miniaturization and the commoditization of the hardware, the transistors. I remember like we talk about these little transceivers that we buy about the size of your finger that actually has a laser transmitter and essentially like a photodiode on the other side that receives the signal and turns it back into an electronic signal. So you can think of it as like a laser and a receiver. Yeah. The components that fit into standard network equipment to interface with fiber when I started were costing, to do 10 gig were costing thousands of dollars, and now they cost like $10. Okay. So actually the enablement of the bandwidth has come from the commoditization of the hardware and the fact that it's so widespread, and in the same way that that drones, like no one ever really asked like where did drones come from. There was a great article in The Economist 10 years ago on this, which was like, why do we suddenly have drones everywhere? And it's all basically because of smartphones. So it's like a really nice case study of like smartphones drove the commoditization and miniaturization for batteries? Like 3-axis, so everything that you needed to make drones work. Okay. So like 3-axis gyroscopes, which are now were quite expensive little chips. And discrete chips now come as a part on a general sensing chip that also can do GPS and can do a bunch of other stuff. Yeah. The GPS chips, we suddenly went from a place where like, I don't know, the global market for 3-axis gyros and GPS chips was, I don't know, a few million devices a year, and suddenly everyone has a smartphone and it jumped to like 1 billion a year. And so the economics of manufacturing them just dropped. And it was the same with the batteries that we have in smartphones. We went to lithium ion, and then like we got better production with that, and so a lot of the tech that actually makes drones work, which is like super lightweight motors, lightweight high density batteries, and critically the gyros that make them easy to fly. All of these components were basically just driven by the mass market for smartphones, and then suddenly drones appeared, and it's like it's completely black and white.
Yeah. So we've got drones because everyone wanted to measure their step tracking on their phone, exactly. and because they wanted to watch TikTok longer, basically.
Yeah. So like you can clearly draw those lines, and it's kind of the same with like a lot of the network technology. So as we've kind of networked more and more things, and fiber has really dominated in the network space, the commoditization of the componentry has like made that a lot more accessible. And then I think to your question about like the kind of theoretical capacity of the fiber, then it's just really about like what does it cost. The cables themselves have not really changed in the last 20 years. Really? Yeah, and that's one of the reasons why, like for us, like investing in a fiber network, as in a physical fiber network, is a kind of a really, really safe bet. It's we can continue to, and we know today, like I can buy equipment that costs 100 times what we currently spend, and I can put 20 to 100 times more bandwidth down an existing cable. It's not a constraint of the cable, it's just that the equipment's mega expensive.
Got you. So it makes it more accessible for, say, a disruptor to jump into the market and know that it can't be dominated by a monopoly company right now that has better access to not technology, but better access to the materials, better access to fiber.
Yeah, I mean the fiber, it's not. That's not really the constraint. Is I guess the interesting part. It's literally like the kind of the capex of the equipment that you're going to put on the end of it, and how much you can aggregate. And then you get into some interesting economics, which is like it would be a bit like building a bridge. You could decide to build like a very, very small narrow bridge, to span something. And if you think about like the cost of the bridge is basically how big is the span. If you want to get more traffic flow, then you're kind of incentivized to think about like rail or high speed or whatever. But if it's a really small gap you're spanning, then you might just build a fatter bridge with more lanes on it, right?
Yeah. Okay.
Yeah.
And so you get into this like weird, you get like weirdly incentivized that on short distances, like in metro areas, to just put more fiber in the ground because the transmission equipment is essentially, the difference in transmission equipment is cheaper. But if you're doing transatlantic, you actually run relatively few fibers and you spend a lot of money on your transmission equipment.
Okay.
Because actually that the economics start to work better over thousands of kilometers. So on short distances, like the fiber's kind of trivial, it's inexpensive, you don't really think about the cost of it. The same way you don't probably think about the cost of like a network cable in your house. It doesn't really matter.
Yeah.
It's funny how much the word incentives is coming up here, and I think this will be relevant when we talk about Web3 a bit as well. But
it's all economically driven, right?
Yeah.
So you get to a point where whatever it was 10, 15 years ago, Google's paying enough to use space on other people's cables, and the traffic paths are inefficient that Google starts laying their own subsea cables, which is insane, right? You've got like essentially what is like a search engine advertising business is like contracting cable laying ships and putting cables under the ocean to essentially, to sort of the point you made earlier, like start to find efficiencies, like to bypass the normal paid route. It's like if we were, and it's very, very simple, if you and I were sending so much mail to Singapore that it was like costing too much, we might start thinking, well, why don't we just rent our own plane?
Yeah,
exactly.
We'll charter our own flight and we'll ship it all directly ourselves.
Like vertically integrating the internet basically for themselves. Yeah.
And one element of that this kind of bridges to is when people think of fiber, broadband, internet, and this kind of overlaps with Web3 and something that a lot of our listeners will be interested in, is the idea of privacy. And I guess that is something that's kind of come into the public limelight in the last 15 years, maybe. And I've heard you talk about kind of what kicked this all off, maybe with the Snowden case. And I really want to know what your position is on this stuff and what Vorboss is doing.
Yeah, okay.
Reluctantly, maybe.
Rabbit hole open.
The worst part is I couldn't help smiling as you were asking the question. No, I think it's really, I think what's really interesting is in the same way that if you send a piece of mail, it probably occurs to you that the government can open it if they want and probably will if it's necessary, and also that you probably wouldn't have any way to know.
Yeah.
Right? And I think your digital communications are broadly no different. I think what's for me the biggest dissonance is like the lack of awareness. Like I think people would be very surprised if they understood the sort of scale and breadth of how much of this can be done and is being done versus what they perceive to be the level of privacy that they have. I think then the even scarier part is in the UK in particular, the breadth of legal power to do it is probably more than people. Like if you stop people on the street and kind of a little bit leading question, like, does the government have the power to do this,
Yeah.
Yes, no, yes, no, yes, no. Like and you gave them kind of a sequence of questions. I think you would find like 90% of people are unaware, if not probably more than that, of just how much ability there is to intercept communications, and actually...
Yeah, and appetite as well, right? Because I think the recent, UK government trying to get this backdoor into Apple and iCloud and things. I think that opened a lot of people's eyes that they were like, I didn't realise this was on the government's agenda, but it clearly is, right? They want to be able to potentially...
Yeah, and I think those sorts of surveillance powers are like really troubling, right? And I think there's still an open question, and I'm not close enough to it to really have got into it, of like, do they just fundamentally not understand the problem with that, which is that you've fundamentally broken the technology if you request a backdoor, or do they fully understand the implications of it, but they want it anyway? And I think that's really problematic.
And do you think this is all true and still holds in this kind of like post-Snowden encryption age where, from sending to receiving, there's an encryption in the middle, and more we're seeing device-level encryption, with the advent and perpetuation of like enclave and, secure enclave on the device to ensure that my message is encrypted and that secure enclave can't move from my device. Do you think that's still the case, that they can intercept whatever they want?
Well, like there's some like there's some really, really good security podcasts, right? But I think you have to start from the premise that like all security can be broken, like everything can be broken. So really all you're ever doing is like, it's what's the old thing of like, you can build a 12-foot wall and I'll just get a 13-foot ladder. It's like it doesn't really all you're doing is adding like friction. So you're, and in the same way that physical security around your house, I was sort of recently in South Africa, and it's really interesting watching, seeing like the size of walls and barbed wire and electric fences, and you go down the street and you're like, is any of it really necessary? But what's clear is if you're the guy that has nothing, you're definitely the guy getting robbed. And so you can see there's probably a bit of an escalation of like, because I'm looking at all of that and I'm going, well, it really wouldn't be that hard to just like climb that wall, disable that electric fence.
What an interesting perception that is, to go there and be like, I could rob that place.
No, but like you look at it and you're like, I guess maybe it makes people feel good, but it's kind of crap security. Some rubber gloves and bolt cutters, you cut the electric fence, you lean a ladder against the wall and you're in. It's really not hard.
We don't advocate this position, by the way.
No, but so you kind of start wondering, like, well, so why are they doing it? And it's like, well, because I guess the answer is like, you just need to make your place harder. I don't need to be able to outrun the bear. I just need to be able to outrun you.
Yeah, it's a signaling thing as well, isn't it? Like I'm a fitter competition than this other guy over here.
And it might make you feel good, right? Okay. But like the practical, so it's really no different with digital security, right? Like you can. And that was, I think the only interesting thing is like people like me were kind of getting accused of being a bit tinfoil hat. And I think what Snowden showed, rightly or wrongly with his disclosures, what he showed was that like the ultra paranoid were probably not paranoid enough. And I think to put that in perspective, like one of the ones that's like just my sort of favorite because it's so visceral is you could do all this stuff, right? But how do you know that your laptop wasn't intercepted before you bought it?
Yeah.
And how do you know, and so the NSA was doing this, right? So the NSA was intercepting network equipment that was going into networks. So they were intercepting, they basically worked with a courier company that was delivering network equipment into core networks. They built a facility, and there were photos of this in the leaks. They built a facility where they had all the original packaging from the vendor. Now, whether or not the vendor knew, or who knows? But again, under the law at the time, they could have compelled the vendor to comply and given them an implicit gagging order to prevent them from disclosing that they had complied. So it's sort of irrelevant, right? Like, it's not hard to imagine that the NSA could probably also just make their own cardboard boxes, like, and make it look original. But you can imagine, right, the difficult position it puts networks in, which is like, no one's probably paranoid enough to think, like, okay, I ordered $1 million worth of routers for my core network, and actually they got intercepted on the way in. Physical implants were installed in them, and then the warranty stickers were put back on. So, like, what are you going to do? You're going to open it and have a look? Are you going to X-ray it? How would you even know?
Yeah, exactly.
Whether it's been altered. And in fact, if you do, you actually might have done something illegal. So this is kind of the problem, is you have to sort of go, okay, well, certainly as pertains to nation states, you basically don't have, you don't have much defense, really. But this was really happening. They had a whole facility, literally like take stuff, unbox it, modify the equipment, and then repackage it and send it out to the end users.
So as for my secure enclave security, it could mean nothing if that device is intercepted.
100%. And I think that's really the big risk. And there's been a few kind of these supply chain kind of attacks that have been reported. Some maybe turned out to be nothing. There was a big scare around Supermicro a couple of years ago around they had a supply chain attack of this type. Again, it's like this is pretty mundane, right? Like if you assume, you think about like how long ago those Snowden leaks were, and clearly everyone was up to it. So like what's happened in the decade since, right? Like, but it's obviously become like more sophisticated, probably with more vendor engagement, and not because the vendors, I have to sort of be very quick to say, not because the vendors necessarily want to be engaged, but because they might be being compelled to be engaged, right? And so that's very, very difficult. And so to your question about end-to-end encryption, the problem is absolutely the old school way, like pre-Snowden, basically everyone just thought it was too much. Essentially, if you ask like smart people who ran these networks, they go, oh, it's just too much hassle to like intercept fiber, to like and intercept traffic. Well, it turns out various governments disagreed, right? They thought it was well worth the hassle. So you had these huge, like, you can imagine like there's like a cable landing stations. We've got the Subsea Cable, which is like a really nice choke point for all this traffic that goes like from Europe to North America. There's only a handful of places where this lands, as opposed to like the rest of the internet, where there's hundreds of places where traffic is interchanged. So you had in the UK a couple of cable landing stations, and then the sort of project that you can't imagine went completely unnoticed. Big cable comes in, and it has to be terminated in a very special way, subsea cables. And then it lands on a much more kind of mundane run-of-the-mill cable that then takes it from the kind of coast into London, into the major cities. And like at that point, they intercept it with another massive fibre cable that basically heads off to GCHQ. And they go, we'll just take a copy of all of that. Right. And that was like an actual thing. And BT did it for them, right? Like this is, I guess all legally, but it happened. In North America, we had the same problem. So you had massive cable taps so you had operators like Google had, this came out of Snowden, massive trunk fiber cables between their various data centers. That they're running their Google Compute Cloud, and the same would have been true for Amazon, right? Like all the cables that run between their data centers. No one used to encrypt that because you're like, well, we literally paid to have the cable put in ourselves. It runs 200 miles between this big data center and that big data center. We put tons of traffic over it. It's all basically private. You think of it like running a network cable across your house or across your. Imagine going from like your house to your shed. You sort of don't imagine. Like perhaps foolishly, you don't imagine that's going to get tapped. Well, all of that was being tapped. They were just finding a site somewhere in the middle, digging it up, presumably at night time, whatever, tapping the cable, and then taking all the traffic off somewhere else. There's precedent that this was even happening with submarines, right? So you can go with a submarine, you can like go over a subsea cable, lift it up inside the submarine, tap the cable, pop it back down, lay a new cable along, tap it somewhere else. So we had this like happening everywhere. And then in Germany, at Decentralised, which is the German kind of internet exchange, so you get these kind of internet exchange points where lots of operators agree to exchange traffic for no charge. So you get like 1,000 operators all pop up and say, okay, well, we're all going to go to Frankfurt and exchange traffic. A bit like having lots of airlines at the airport, right? And again, the German government decided that was a really great place to just dump all the traffic from Decentralised. Massive. That was post Snowden that leaked, and I forget which specific leak it was. But that was a really big deal. Yeah. And the argument was that that at that point it's all like public traffic. It's all because it's on the internet.
Right. Yeah.
Everyone should be treating it as untrusted anyway. It's like writing on your postcard. Once it's kind of left, once you've put it in the mailbox, you pretty much know anyone can read it.
Okay.
And so I think it's one thing if it's like traffic between like your house and your shed. I think once you've tossed it over the fence, you sort of probably do have to assume, and that's where end-to-end encryption comes in. But anyway, so you had this like idea that they were tapping the major German internet exchange. The real issue around that was it was all bulk surveillance, and all these things we talked about essentially are some form of bulk surveillance, and that's where people start to get a bit itchy. We're all a little bit more comfortable with the stuff we see on TV, which is like targeted surveillance. It's like that one terrorist, and we're gonna like tap their communications. But when you start basically just having this like dragnet of catching everything, that starts to become more problematic. And I think with AI, that becomes even more problematic because the problem used to be, they used to always defend it. We don't do that kind of surveillance because there's just too much data. You can't find the needle in the haystack. It was like,
it's becoming easier.
Got to wonder like how much easier that's becoming.
And so with the end-to-end encryption now, obviously some elements of that, it's harder to do. Like there's more privacy preservation. But like you say, to pass between different routers and different providers, you need a degree of metadata, you need a degree of like, where is this going? And that in itself is privacy, private information. So, I know Vorboss, you have this ultra secure, is it direct private connections? Does that remove the element of that? Is it like if I'm now connecting directly from my house to my shed with one single line, there's a bit more privacy in that?
So we have some direct connection stuff, which is mostly for cloud interconnect things, and that is, but that's really more about optimal routing, lower latency, and dedicated bandwidth. Okay. And actually, then also being able to put SLAs over all of this. Okay. So again, it's being able to say, okay, well, the advantage of putting your postcard on a private plane to Singapore is that the operator of that plane can guarantee that they'll get it there within 24 hours, and if not, you get your money back.
Yeah, right.
Royal Mail isn't going to give you that guarantee. So the kind of the public internet is sort of always best efforts. Whereas when we take more control over the traffic path for a premium, we can provide certain guarantees around quality of service. So that's what that element is more about.
Okay.
If the data is sensitive, then the end user should always encrypt it. And actually, almost by definition, from everything I've just told you, you can't trust me to encrypt it for you.
Yeah.
You can't trust anyone to encrypt
Defeats
it for
the
you.
purpose,
Like, you never should trust, like that's like,
Don't trust anyone ever.
yeah, you can't, right? In the same way that, with like crypto wallets, you don't,
Yeah.
all of the major issues is when you've trusted an exchange to hold it for you.
Yeah.
And then, rather than, at least if it's in your own wallet and you get hacked, it's your own fault.
Yeah.
And I think that's kind of the distinction.
Yeah.
The interesting thing with end-to-end is, so there's the metadata leakage, which is there are plenty of people who have been arrested because what they're able to do is figure out who was messaging who. They can't read the message, but you can tell where the interconnect was. So that allows you to take down like criminal networks, for example, where like they're clearly all messaging each other at the same time at 3 in the morning, and then like and then in with that metadata, we can do things like figure out where your phone was at the time. So we can see when you were being messaged to coordinate something, and then we can go back through a different channel and figure out what, based on the mobile network records, where your phone was. And that kind of metadata might start to become, very interesting. It's like the thing of like, there's a great talk from like a hacker conference, which was on the sensitivity of metadata. And like they've got these examples of like, we don't know about his mental state, but we know he was stood on a bridge at 3 a.m. calling the Samaritans.
Yeah, it can be as usful as the actual.
You don't really need to know the contents of that call to understand what was going on. And I think, so that's the power. The problem though with end-to-end encryption is like the other way that gets solved is that then you just need to target the end device. So that's either I need to just look over your shoulder, or I need to take the device off you, or I need to implant the device before you have it so that you think it's secure but it isn't. So I can read the message once it's decrypted on your device.
Okay.
And this was the way a whole bunch of messages got hacked by some of the malware that the Israelis developed, for example, and that was getting sold into a bunch of places where actually that's what, for targeted surveillance, that's all that's happening now, is that you just basically compromise the device, and then at the point of the message on your screen, it's decrypted.
And this is all assuming that there's no backdoor that the NSA knows to the encryption algorithms to begin with, anyway, right? It's a bit of a depressing picture overall, I think.
Yeah, I guess my point is that, like, for targeted surveillance, why bother with the backdoor? Because it's just easier to compromise the device.
There's always an easier way than the theoretically most secure part of the system is not where it's going to get broken, is it?
Yeah, 100%. And so we're back to like walls and ladders. It's like you can do these things, And just this week, there's been there's a little publication from a guy about CPU microcode attacks, which is this idea that like pretty much since like the late 90s, all the CPUs that go into modern computers are so complicated that they basically have microcode, which is a kind of what like Intel, AMD and others, they can put a little bit of code onto the chip at a mega low level to change some of the behavior of the chip, or even to turn off features inside the chip, usually to get around manufacturing defects. So that the microcode really exists, and so it was never really thought of as like a mechanism for improving like the hardware or a mechanism for attacking the hardware. And it was really, the keys to that is sort of super tightly held. But the idea is that you can have microcode on the chip that is modifying the behavior of the chip. And there was a proof of concept that showed that using a microcode attack, they could modify a processor, a very common off-the-shelf processor used in millions of devices, to always return the number 4 when you request a random number.
Wow.
and so like you can do whatever you want in your software stack above that. So this is sitting like well below the operating system.
Yeah.
This is
so most people wouldn't be aware of it.
Well, there's just no way to know that had been done. That's an interface that's super low level that they had basically reverse engineered, figured out, and then modified the behavior of of how the microprocessor is operating. And so you sort of think like, okay, and if a researcher can do this, what can nation states with more resources do?
Yeah, it sounds like a quite depressing picture for me. Like it sounds like we've got no hope at any level of the stack. And I'm conscious we could talk about lots of the issues with the internet and our security all day. But as we're kind of coming close to the end of this episode, and I think we'll probably have to have a few more to cover these other topics, but I'm conscious that we've kind of hinted at the internet and privacy now, and Web3 is obviously, we're a Web3 podcast, and this is kind of where they meet in some sense. There's lots of debate over what it actually means, and I'd be interested to get your take. But from an infrastructure perspective, what do you think the implications are for and by Web3. Do you think this movement that people are working towards a Web3 is going to require new infrastructure? Do you see it operating at just kind of the application layer? Like, I'm curious, like as someone who is a practitioner in Web2 effectively, what do you think about the changes coming with this?
Yeah, I think like someone referred to it as like deep infrastructure recently. I was like, oh,
yeah.
no. It's like
it's way higher probably. Yeah,
it's quite shallow still. No, but I think I'm like kind of optimistic, amazed, and also slightly terrified, right? Like there is a bit of an issue with, what we always do with technology is abstract. So even with, look at like AI coding now, like, the argument is you don't need really to have like a ton of ability to, like, as a computer scientist or algorithmic knowledge to write software or to build things. And that's amazing. And I think we see that trend with a lot of technology, and Web3 is just kind of an iteration there, right? Which is sort of whether we can abstract a lot of stuff over the top. I think where it gets difficult is when you have some of the kind of Web3 evangelists, and I got into a few arguments at early doors around things like Bitcoin and distributed blockchains and distributed ledgers, and like this idea that it's like a panacea, and it's like, yeah, but it's still built on top of this like legacy internet that isn't physically changing. You can sort of abstract to a level that you're no longer really having to think about where the cables go and who the operators are, but like fundamentally it's all still there. Like that's how it's all working, and it's insanely fragile. We talked about these kind of routing tables, right? So your packet, when you're sending that WhatsApp message, gets to a global router, and it then understands the next hop based on a list of a few million destinations possible. That's all trust-based, largely. So we get, every few months we get, you may have seen these and Google it, by all means, a BGP attack. And these can either be malicious or accidental, quite often accidental, where essentially those tables get poisoned. So a network somewhere in the world randomly, just by accident, like fat fingers something and starts announcing a route that then makes it into the tables, the global tables of all these routers, and then they start sending packets to the wrong destination. There are also the malicious versions, like when the North Koreans just randomly announced that they were a valid destination for lots of traffic that wasn't them. So loads of traffic ended up going to North Korea that shouldn't have, and then getting spun around. But in the meantime, they were able to just like hoover it all up and monitor it, right? It's literally like diverting the plane. Like your postcard ended up on the wrong plane and went via North Korea, still ended up in Singapore. But for like 40 minutes, all this traffic went through a North Korean network.
I think people will be surprised by how dependent we are on third parties still in the internet, like the certificate authorities, the DigiNotar hack and things like that. Like things can just go wrong very quickly. But even when people then talk about Web3 and think, oh, this is, as you say, a panacea, this will solve everything. They say, well, why is it good? Well, Bitcoin's decentralized. And you say, well, it's all being run by AWS. Everyone's running their infrastructure in the same place.
This is kind of like the things that I worry about is like this. So the decentralization stuff, like that's interesting because a lot of the ability to operate these like free and kind of accessible systems comes from the fact that we are in like nominally quite free countries. You can't engage with Web3 inside North Korea. So actually, what's really interesting is if you have this like real kind of what's the word I'm looking for? But like anti-establishment. There is I guess what I always find really hard to reconcile when I sit in some of these talks is like there is sometimes a real like anti-establishment vibe around people engaged in like Web3 stuff and blockchains, and you're like, yeah, but the whole reason it works is that you live in country and hopefully pay the taxes in the country. That means that you have a military that provides a deterrent to mean that your borders are actually worth something. And if you don't have that, like, well, you sure as shit don't have the internet, and you don't have free access to the internet, and you probably don't have the ability to use encryption. And actually this is where it gets really interesting, is like a lot of the fundamentals, like if they're going to start saying, well, we need to be able to read your WhatsApps, then actually why should you be, blockchain essentially gives you a form of encryption around your wallets, things like that. Like why should you be allowed that kind of encryption? Like why is that any different? And actually, well, why don't we just start encoding messages to each other using crypto wallets, because actually we could come up with a method for doing it where we say, oh, it's not actually a messaging platform. There's all sorts of like, it's kind of nonsense. So that if you eventually get to a place where you say we have to ban encryption for consumers, and some countries do that. They say, well, you can only use encryption up to a level that the government can break. Which is in itself again like really problematic. So what I would say is like there's kind of this thing about like nations, sovereignty, borders, like if you strip it all away, like you do need these things. And then to your point, it's like certificates and certificate authorities and how that works, where like it all depends on a load of infrastructure that's either like very commercial or very centralized. And I think it was always interesting to me, like, you know, that how long it was going to take before hedge funds started trading crypto, because they realized that all the same tricks they were using for high frequency trading would actually work with crypto as well, right? Like if you could procure lower latency connections and you could see the network consensus before others, then actually that's something you can take advantage of.
Yes, so you actually talk a little bit about this. I remember we had a conversation you were talking about, I think you were at a conference or something like this, and someone was talking about this decentralized exchange or something like this, and you were like, yeah, well, if I run the piping to that and I get like slightly lower latency on the price value and all this kind of stuff, I can front run you and make a lot of money. Can you talk a little? Because I think I'll really emphasize the point about how decentralized some of these applications actually are.
Yeah, so I mean, I remember the specific episode. So it was this would have been over 10 years ago. So it was very early days of the Ethereum network, I think. And so it was probably the first. It was like the same week that I'd learned about smart contracts. I think it was like we were all like quickly reading up, being like, "Holy what's this stuff?" Right? And then everyone's like, "Oh, it's like a big distributed supercomputer." And like, well, it's definitely not that, but like, let's keep going. Like, and so this one of the panelists at this conference was saying, you know, this is the thing that will like break Uber. He's like, in the future, imagine there will be in London. You know, we're sitting in the center of London for this thing. He's like, in London there will be there'll be a load of taxis, maybe even robot taxis, like whatever. And I'll be able to or a taxi driver will be able to have a smart contract that will basically, like, when a rider wants to travel somewhere, just like Uber, you'll be able to issue a smart contract onto the blockchain, and then you'll be able to bid for it as an operator, as a driver, and you can then win the contract and then go and complete the journey for them. And they're like, this is amazing because there won't need to be an Uber anymore. So it was like this kind of decentralization panacea, and it came with it was laced with a little bit of like anti-capitalist like mentality of like the big companies and all this. Like, it's all evil, and you're like, okay, hang on a minute. Yeah. So I was like, well, let's just think that through for a second. And I was like, so unfortunately, I just sort of had my hand up, and I was like, I'm just going to call BS on this. Like, okay, so the cab, how's the cab connected then? And they started like waving and saying like 5G is going to be ultra low latency. I was like, okay, cool. It's still going to be higher latency than just physically being at the base station. So like there's a limited number of base stations. Those will aggregate back to a limited number of sites. Those then get their internet connection from somewhere. So like if I actually think about the flow of information, like the rider has a phone or whatever, they publish a journey. Okay, where's the first point that hits the internet? It's like in a data center somewhere where it then like hits your distributed ledger and blah, blah, blah. And then eventually like that message goes back into the network that's delivering the message back down to the cab driver. I was like, my point was like, all that will happen is that someone like me or like some smart people will come along and just stick a server in the data center that these networks are in, and I'll write a smart contract that says I'll just scalp all the journeys that riders have and I'll bid on them immediately, and then I'll reissue the tickets back into the network at plus 10% for the drivers. And I'll be able to do it because I have the information before they have the information.
Yep.
And actually what you'll start to have is like I'll basically be able to build myself a little cab company. Like I'll be dispatching cabs based around like getting the rider information. I was like, you will literally just recreate the same thing, and it's because of the inability to like overcome the sort of fundamental physics of the situation, which is like where the information actually flows. Until the rider is like, the only way that would work is if the rider is able to like, you know, it's like the almost like the off-book version, which is like when I hail a black cab with my hand, like no one knows about it. That information is like low latency between me and them. And like, unless you have a technology to deliver that, like unless the radio on my phone is going to communicate with the cab directly, and so the network at the data center finds out last, it doesn't work. And then if you take the same, maybe it's not cab journeys, but it's some other smart contract that has to go across continents, same applies. It goes onto a legacy network of like a giant telco, and then it goes down a long fiber cable that goes under an ocean or through through the Suez Canal or whatever it might be, and like there are these intercept points where if you then pick up traffic at those points, you just learn about it faster than everyone else. And that's the same as the kind of the Flash Boy stuff of like, if you have the lowest latency connection between New York and Chicago, then you can make trades based on information that everyone else doesn't have yet. It's the same old thing.
It always applies. So I mean, we've talked a little bit about how infrastructure overlaps with Web3, and you kind of hinted at AI. Do you get asked about what the overlap between AI and infrastructure is, and maybe things at Vorboss that you're thinking of doing? The mass information that is now can be digested and used for useful outputs. Is it something that you're interested in?
Yes and no. I mean, I think the Vorboss thing. So just to clarify, like what we've built is we've built a metro fiber network. So we've just talked about some of these like long distance, connections with relatively low numbers of fibers. When I think about fiber networks, you can kind of think about the value of a network being the number of routes in the network. So I connect two big cities. I have one route, multiplied by the number of customers there are for that route, which might be like a bunch of really big networks that aggregate traffic. And in a metro network, it's kind of the opposite. We have thousands and thousands and thousands of routes in our network because essentially we need to be able to connect lots of buildings. So we need to be able to connect every single building in London. And then at the end of each of those is a very small number of customers because there's only a small number of tenants in each building on average. So the value of our network is kind of inverted in that like we have thousands of routes, tens of thousands of routes, and then relatively small numbers of customers per route, which makes it kind of a costly network to build per meter. But it is insanely valuable from the point of view of like, you have a pretty exclusive asset. It's all built using, so the other thing you obviously start to realize is that almost like the roots of a tree or something, very quickly once you get outside the building and by the end of the street, the number of fibers we've got is really big. So, we're running cables that are sort of the diameter of your finger that have 864 fibers in them. So back to our cardboard tubes thing, that's a cable that's got like 864 little tubes that we can talk to each customer through, and that cable's good for 25 years. And as I said, we can just keep upgrading the equipment on the end. So I think we sort of fundamentally are quite immune to it because like our role is literally providing that like almost it starts looking like a utility. It's like having an electrical cable into those buildings. I'm not really too worried how you use it. You're going to fundamentally need it, and we're very confident the amount of bandwidth you're going to need is going to keep going up regardless of what the trend is that causes it. So I spend most of my time not worrying so much why people need more bandwidth because I have tons and tons of data that tells me that for the last 100 years, bandwidth consumption has gone up 50% year on year, and I have every reason to believe it will continue to do so, and AI is a driver, but maybe not always for the reasons people think.
Yeah, interesting. I think I've learned a lot about this industry that I didn't know before. I've also learned a little bit more about physics that I didn't know before. So that's been great. I think we should probably. I think this is a good place to end this, coming full circle on what you're doing. I guess anyone can find you at vorboss.com, right? And they can find out more about what you're doing. Is there anything you would like to just highlight about what Vorboss is doing and what's in the future for you guys?
I think, and you can always message me on LinkedIn as well, which is probably a preferred way. I think not really. I think we're pushing really hard in a space where, amazingly, in London there hasn't been much innovation. We have in the UK BT as the former monopoly. And it's been a really, really tough environment to go and do what we've done. It's kind of, you led by saying sort of 250 million. All said and done, we'll have put 300 million pounds in the ground. That's just an insane undertaking. And it is quite difficult to get people to kind of have the belief that there is the need for that. And I always have to remind them of like when you're sitting on a plane flying into London, looking out the window, you look at like all of these businesses and you think now, the internet access for them is probably the most important utility. And that's been a really interesting change because actually, when my mum worked in London in the 70s, there was no internet, right? Like, so you think of like all the stuff that people used to do in an office building day to day didn't involve the internet, whereas now if you pull the internet connection out, everyone has to go home and work from somewhere else. So we've completely fundamentally changed it. And a lot of the networks that were built in, more than 10 years ago just weren't designed for this kind of like criticality. So I don't know. It's not so much a sales pitch as a kind of a
take a step back and be like, wow.
Just a reminder that like and I think there's a couple of like nice quotes on that, which is like the kind of the future's like built by nerds, right? It's like this has been a long project. It's taken us like 7-8 years to get to where we are. That's with like a speed of execution that's like really unusually quick. But we are thinking in timeframes. I'm regularly thinking in timeframes of like, what are we going to need 10 years time? not like what do we need today, because like this stuff is just slow to move. Like we physically have to move Earth to build these things.
Yeah, I think when we first met, one of the things that really stuck with me is that when you looked into this problem, you went to fundamentals and were like, it's not the sexiest sell. It's not the thing that people, typically like when they build a new project, oh, what's the fibre going to be like? But it's one of the most important things. It's so critical, and it often doesn't get maybe the publicity that it deserves. And you really want to deep dive into this problem. Like, how can we make this as good as it can be and ignore all the work that goes into it? Because it's a 10, 25-year pitch to be like, we're going to dig up the ground and put all these fibres in, and we'll start to see the value down the line, rather than some of these apps and products and AI projects all over the place that spin up and say we'll make millions in a year or something like that.
Yeah, and it's for me it's interesting because it's such a fundamental, like it's an enabling technology for all these things, and so it's like it has to be there, and everyone sort of takes it for granted. And in a weird way, like I think that sort of suits our kind of I think we try and be quite humble about it. It's like we don't need credit for it. It's like you don't. I always use the analogy of like you can build like a massive bridge or a Thames crossing or something, and like no one's there taking credit for all the value of the commerce that goes across it. Yeah. That's not really the point, but like you can just be proud that you built a really good bridge. It's like I think we're sort of we like that about the infrastructure we build, is that it just works and it will last London for the next the next 20 years.
Yeah, I think it's people debate whether Web3 is here to stay, but I think no one will debate whether the internet itself is here to stay. So yeah, it looks like you're well set up for the future. But yeah, thank you so much for joining us, Tim. It's been an absolute pleasure to have you on. I'm sure it won't be the last time we have you here. And all that remains to say is to all those listening, thank you for joining us, and you can join us next time to untangle a little more Web3.
Thanks, guys.